So I am here with my friends Tralfaz and Astro, the lobster gummies, for a short episode and demonstration of candy science. Now, if you don't have these materials, do not worry because I'm going to follow this demonstration up with a quick little activity that you can do using common household objects. So I have my 2 red gummies and I have my bowl of finger flashlights right now. So right now I want you to notice what color the gummies look. First when I shine a red light on them, then when I shine a blue light on them, and a green light on them. Do you notice that the gummies obviously cannot look red if a green or blue light is shining on them because there's no red light to reflect at all? But since white light is made up of all of the colors in the visible spectrum, that's when we're able to see objects' true colors based on that principle of selective absorption. Now, because of the white light, we can see the red in the gummies. In contrast to if you shine blue light, there's no red light to reflect, so they can't look red, even though they are red. Okay, so here's a second demonstration to show you the principle of selective absorption. So for this candy science demonstration, I'm going to take Tralfaz and I'm going to take Astro, and I am going to place them side by side because they're the very best of friends and they love each other so much. Now I'm going to take my red finger flashlight and I'm going to put it next to Tralfaz. So notice that Tralfaz and Astro are translucent gummy friends. So the light is able to pass through. So this red light illuminates Astro, passes through, and then also, illuminates Tralfaz, passes through, and then also illuminates Astro over here on this side. I also want you to notice what's happening with that pattern of red light. So what do you think will happen if I take away that red light and I replace it with green? So now notice how Astro over here is not getting illuminated at all. That's because Tralfaz is red and red objects absorb all green light. He's absorbing all the green light, so it cannot get to Astro over here. But what if I change that light to blue? Boop. So notice how the same thing that happened with the green light is now happening with the blue light. That's because due to the principle of selective absorption, red objects absorb all blue light. So that Tralfaz is absorbing all the light and poor Astro over here cannot get illuminated at all. But now what do you think will happen if we change the light source to white? Boop. So notice that the same thing that happened with the red light is now happening with the white light. That's because white light has red light in it. Now the light is passing through Tralfaz and it's able to get to Astro because Tralfaz is no longer absorbing all of the red light that is in that white light. That is because of the principle of selective absorption. Okay, so now our friends Tralfaz and Astro are going to go on lobster holiday because luckily for them, lobsters cannot get coronavirus and they do not need to socially distance. Have a great trip! Okay, so while they are gone, we are going to combine red, green, and blue light in different ways because I think I've already mentioned to some of you that all light is actually made up of red, green, and blue light because those are the only cone receptors that humans have in their eyes. So right now we're going to see what happens when we combine red, green, and blue light to try to find the secondary colors of light if these are the primary colors of light. So we're going to take my white bowl. And first we're going to shine the green light and the blue light in my white bowl. So what color do you think we're going to get when we combine green and blue light? Do you see how it's turning this really nice sort of robin's egg blue, sort of blue color? We call that color cyan. So green and blue together create the color cyan. And obviously, if you change their proportions, you're going to get different shades of that color. Okay, so now let's see what happens if we take our green light and we trade it out for our red light. What color do you think we're going to get when we combine blue and red lights? Let's shine it on my white bowl. And do you see that really pretty pink color? That's the color magenta. So blue and red light, when they combine, make the secondary color of light magenta. Now let's trade out our blue and pick up our green. So now we're combining red and green light. What color do you think we're going to get when we combine red and green? Let's move them together. And let's try to get the exact right proportion. Do you see how the edges of the bowl have now turned yellow? That's because when you combine equal amounts of red and green light, it actually makes yellow. And obviously, as you change the proportion of red to green light, it's going to make different shades ranging from yellow to more tangerine. And using just red, green, and blue light, you can actually make every single color that you've ever seen in your entire life. So you can see that right now I'm getting sort of a like greenish orangey color. Okay, friends, so last but not least, let's combine all three colors of light. So what do you think will happen when we combine red, green, and blue light together? We have our cyan. And now, so the proportions need to be perfect, but now, do you see how certain parts of the bowl now look white? That's because when you combine red, green, and blue light together, it makes pure white, just like when we combine every single color of the rainbow. There it is on the edge of the bowl. Do you see it? And right in the middle, it's actually making white when you combine red, green, and blue. All right, friends, so I told you that I would have an additional activity so that if you do not have finger flashlights, which I highly doubt you do, there are still ways that you can combine red, green, and blue light in different ways. So I'm going to show you that at my desk right now. Okay, friends, so here is how you can combine the primary colors of light with materials that you have at home. So remember that color wheel that we made for lesson 9? Remember how I told you to leave the back blank? Well, now you can fill up your blank back and combine the three primary colors of light in a different way. So for me personally, I think cyan might be my new favorite color. So I made it half green and half blue to see if I could make the color cyan by combining the photons of light, not the actual matter itself. So let's see if it worked. I haven't actually tried this yet. We're going to wind it up and pull. You see that? Oh, I'm so happy it worked. Look, it's cyan. Oh, it's so pretty. That's definitely my new favorite color. It was green and then it was yellow and now it's cyan. Okay, so friends, from home, you can obviously make more than one of these. You can make as many as you want to combine the primary colors of light in any way that you would like. So the reason that you're able to make any color that you've ever seen or will see using the primary colors of light, red, green, and blue, is because the sensors that are in our eyes only detect the frequencies red, green, and blue. So by detecting those three different frequencies in different amounts, we're able to see every single color. And of course, different animals have different sensors depending on what they need to survive in their environment. So for example, dragonflies need to see many more colors than us in order to survive. So they actually have over 100 different cone receptors in their eyes for sensing even more colors of light, which is really cool. That's really cool to imagine what it must like to be a dragonfly and to feel the wind on your wings and to be seeing all these different shades of light. I wonder how time moves for them. Do you think that time moves slower for them? Do you think they see everything in slow motion? Anyway, that's off topic. But anyway, for your color wheel, I made mine half and half, but you can get creative. So maybe you want to see if you can make the color magenta by combining half red and half blue. Maybe you want to see if you can make the color white by combining 1/3 green, 1/3 blue, and 1/3 red. Or maybe you want to divide your pie into eighths, and maybe you want to make it 3/8 green, 3/8 blue, and then 2/8 red to see what color that you're going to get to try to prove to yourself, if you don't believe Miss Cat, that yes, actually every single color that you've ever seen or will see will be made by combining red, green, and blue in different ways. Okay, I hope you have a lot of fun with this optional extension activity. Please email anything that you make to me, or you can make a quick video or take a quick picture of anything that you make. If you want to share, you of course do not have to share. But anyway, I hope that you have a lot of fun with this, and I will see you soon. That has been Candy Cyan.